Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Hartini binti Saad. I'm from Kolej Yayasan Pelajaran Johor. My presentation today titled Electrical Characterization of Graphene Nanoparticles Conductive Ink Using TPU Substrate. This is the content of my presentation today. Started with introduction and ending with the conclusion. Conductive ink is an ink that results in a printed object which conducts electricity. It is typically created by infusing graphite or other conductive materials into ink. According to the Al-Hawli, conductive ink is a thermoplastic viscous material that conducts electricity by inculcating conductive materials. It can be formulated by blending either nanoparticles or micron-sized particles that are highly conductive, such as silver, copper, and carbon, as shown in Figure 1. Figure 2 shows types of polymer matrix. Polymer matrix can be divided by thermostat and thermoplastic. Printed electronics refers to a type of electronics that are created by conventional printing technologies and receive tremendous attention in recent years. Purpose of printed electronics is to replace the standard of PCB with solder interconnect to flexible and stretchable substrate with conductive ink circuit. Figure 3 shows the comparison of printed electronic between conventional and printed. Conventional printed electronic have a high fabrication cost, complex fabrication process, large environmental pollution, and a rigid electronic, while printed extremely low fabrication cost, simple fabrication process, extremely low environmental pollution, thin, light, and flexible electronics. The concept of printing technologies is to spread and pattern the ink or paste directly on the substrate with the help specific printing. Most researchers studied the effect of conductive ink for silver nanoparticles by implementing and measurement techniques to conductive ink to maximize the quality and reliability of conductive ink. Current conductive ink, silver and copper, is very expensive, oxidation, and heavy. Graphene as the conductive filler proposed because it has strong mechanical properties, light in weight, form conductive networks easily, resist the oxidation. By investigate an electrical characterization of graphene nanoparticles conductive ink using TPU. The objective of this research is to investigate electrical characterization of different patterns and width for graphene nanoparticles conductive ink. For the scope, only consists of graphene nanoparticles for conductive ink, sheet resistivity parameters, 4 different patterns which are straight line, curve, square, and zigzag of 1 mm, 2 mm, and 3 mm of width. The electrical conductivity value of the composite material will increase many orders of magnitude when the composite material reach the pre-collision threshold, and the composite material becomes a conductive composite material. According to RAM, pre-collision threshold value is depend on the characteristic, shape, and size of the conductive filler. In addition, behavior appears because of the filler is forming the path parallelly into the dielectric materials. Table 1 shows the pre-collision threshold of carbon-based materials reinforced with different polymer resins. Pre-collision threshold indicate that the transformation of borderline between bulk insulator and to bulk conductor polymer. The minimum pre-collision threshold is give if given by graphene composites because graphene is lightweight material and has low density. Plenty of graphenes can be added into the formulation and the percolation becomes very small until the electron can easily move to other location and the conductivity become higher. Methodology of research consists of the components of conductive: mixing method, printing method, curing process, electrical test characterization, data analysis, and writing paper. In this research, manual stencil printing method was used as a printing method and TPU as a substrate. The graphene conductive ink was used as the material and printed in 4 different test patterns as shown in figure 6. All the test patterns represent the electrical connection with different directional angles. The sample preparation was started with cutting the substrate with the dimension of 15 cm times by 4 cm. Then the TPU was placed at the back of the stencil using cellophane tape. After that, the conductive inks were separated out onto the back of the stencil. Finally, the TPU was then being taken off from the stencil. There was 3 samples for each stencil and width. Therefore, about 36 samples with different patterns and widths has been produced. The sheet resistance determined by Jandal in line for 4-point probe as shown in figure 8, with 1 mm distance between each probe using ASTM F390 test standard as reference. Figure 9 shows the measurement points on the sample. Based on figure 10, the width of 1 mm shows that the lowest values of sheet resistivity and the lowest value of the error bar. It proves that the data is gathered closely around the average and the width 1 mm for straight line and has lowest and stable average resistivity, while the highest value of sheet resistivity and error bars are at the 2 mm width. The error bars is the figure shows that standard deviation of the values. Phillips' findings ratio was increased. The low carbon content becomes substantially less conductivity by comparison. Given the higher polymer content, a higher resistivity would be expected across the full range. Part of this may be due to the difficulty in obtaining representative ink film thickness measured for the inks. Note that the standard deviation takes into account variance in both sheet resistance thickness measured. Figure 11 shows sheet resistivity for different widths of curve pattern. By referring to the figure, the low sheet resistivity readings are at 1 mm width, followed by 3 mm width, and the highest sheet resistivity readings are at 2 mm width. The lower value of the sheet resistivity depends on the nature of the materials as discussed earlier. The increase and decrease of the sheet resistivity depends on the nature of material, and the physical shape of pattern affects the resistance of sample. Nevertheless, the lowest value as standard deviation will cause the good performance on the electrical conductivity of graphene's ink. Figure 12 shows the sheet resistivity against point of filler loading for graphene inks for 3 types of width: 1 mm, 2 mm, and 3 mm for the square pattern. In general, the sheet resistivity of the ink increases with the decrease of conductivity of the material. By referring to the figure 4, the graph of 1 mm width has the lowest sheet resistivity readings. Kuzaima, a significant difference between resistivity of 1 mm circuit width to the other circuit width was also noticed from the experiment result, indicating lower electrical conductivity performance by commercial conductive paste when thinner circuit width is applied. This illustrates data is gathered closely around the average, followed by 3 mm width graph, and highest sheet resistivity readings are at 2 mm width. It shows that data at 2 mm width spread widely from the average and indicates that they have highest average readings. Figure 13 shows the sheet resistivity at different widths for the zigzag pattern. Based on the figure, the lowest sheet resistivity is at 1 mm width, followed by 2 mm width, and the highest sheet resistivity at 3 mm width. The relationship shows that sheet resistivity of the pattern decreases when the width of the pattern is increased. Saad findings sheet resistivity increase by increasing the width of the samples from 1 mm width to 2 mm, and for 3 mm width, sheet resistivity decreased slightly. Based on this observation, a 1 mm width for zigzag pattern gives the best performance of electrical conductivity. Figures 14 display sheet resistivity against different patterns for 1 mm width. Based on observation, the lowest graph is on the straight line pattern. This shows that the lowest sheet resistivity of 1 mm width is a straight line pattern, and the highest sheet resistivity readings at the zigzag pattern. Sheet resistivity lowest value at 1 mm width is similar findings was recorded where it is observed that the smaller the width, the value of the sheet resistivity decrease because the resistance is the opposition to the flow of electrons through the material is respond to an applied voltage. Therefore, the straight line patterns give the best performance of electrical conductivity for 1 mm width. Figure 15 shows the graph of sheet resistivity at the different pattern for 2 mm of width. The lowest graph of sheet resistivity is in the zigzag pattern from observation. The zigzag pattern gives the best performance of electrical conductivity for 2 mm. The result revealed that zigzag pattern gives the best performance of electrical conductivity for 2 mm width. The sheet resistivity of zigzag pattern decreases with the increase of width, and the inherent conductivity of the printed ink. The performance of a printed line is dictated by its geometry. According to Abu Khalaf, the 2 mm width of curve pattern printed in one layer of silver conductive ink indicate an initial resistance of 40 ohm at 0 strain and reach 279 ohms at 16% strain and start to decrease to 45 ohm after the load removed. At no load, the measured initial resistance is 32.8 ohm and up to 664 ohms as the circuit is gradually loaded to strain for straight line pattern. Figure 16 shows the sheet's resistivity against 3 mm width at 3 different points for different types of patterns. The result of the graph reveals the sheet resistivity for square pattern is the lowest as compared to a straight line, curve, and zigzag patterns. The width of 3 mm for the square pattern gives the best performance of electrical conductivity because the decrease of the sheet resistivity produces the best performance of electrical conductivity. In other words, the resistivity is directly proportional to the temperature of the material, and the conductivity of material is inverse to the resistivity. As conclusion, the electric characteristic of graphene nanoparticles conductive ink was observed based on different patterns and widths. 1 mm circuit width showed significant differentiates resistivity compared to 2 mm and 3 mm width. This revealed that the carbon-based conductive paste is more suitable for wider size circuit geometry application as compared to fine size circuit geometry. The result analysis showed that the usage of graphene will increase the electrical performance of conductive ink, making it suitable for large scale of application such as electromagnetic shielding, electronics components, and electrodes for rechargeable batteries, capacitors, sensors, and actuators in comparison to existing conductive ink in terms of the best performance of electrical conductivity. Future study can be made to observe the difference in the mechanical and physical characteristics of graphene nanoparticle conductive ink, which further optimize its usage in industrial sector. Thank you for listening.